So welcome back to the aerodynamics class. Today we will discuss about the energy equation. Right. So we know that for incompressible flow, where the density is constant, and we already have the parameters like pressure and velocity, right? Also, in the last two classes, we had a discussion on continuity and momentum equation, right? So, continuity and momentum equation already have the unknowns, pressure and the velocity that we need to find, right? So, if we include the density, that is the compressibility effect, we will have three unknowns. Respective unknowns are the density, velocity, and the pressure. But we need an additional fundamental equation to solve this, right? And to find the variables. So we need to derive another equation, right? Another fundamental equation. Hence, we start with the energy equation. In the energy equation, we will have other parameters also involved, especially internal energy and the temperature. That is what we need to think. While you do some energy calculation, or if the temperature is involved, in the case of computational fluid dynamics later, you will enable the energy equation in the code, right? So let us start the energy equation, right? So I acknowledge John D. Anderson's Fundamentals of Aerodynamics, right? So let us start with the physical principle, right? What is the physical principle? The conservation of energy as a physical. The physical principle. The physical principle is the energy can neither be created nor be destroyed. It can change. It can only change from one form to another, right? So we can say that energy can be neither created nor destroyed, but it can be converted into from one form to another, right? So this is what our basic energy physical principle, right? So let us start with the discussion. We already know that the temperature term is involved. So when the temperature term is involved, we need to think about the thermodynamic equations, right? Again, let us consider, say there is a closed boundary, right? And we can say that this is a system, and the system is surrounded by the surroundings, right? Surrounded by the surroundings. So we know that there is lot of matter which can define this system, right? So because of the molecules and the atoms within this system are constantly in motion, there exists a certain amount of energy, right? Say we can say that the certain amount of energy can be expressed by E, Okay. So the certain amount of energy E is denoted by internal energy. Denoted by internal energy, right? So usually we express this E as internal energy per unit mass. Okay. Now the region outside the system is called surroundings, right? Anywhere around the system. So let us say we add an heat. Say, let us say an incremental amount of heat, right? This is incremental amount of heat. So we supply a heat from the surrounding to the system, right? So when you supply a heat to the system, what happens is there is a work done. Let us say del W is the work done, right? On the system, work done on the system by the surroundings. So what is that? You see, usually we used to boil the water, right? If you have a utensil, the utensil is a system where you have water, right? And the surrounding is the boundary. And in the base, you are supplying a heat. And what happens is it start boiling, right? The temperature will keep on increase and it start boiling. And the work done there is converting the water into vapor, right? That's all we need to remember. So del W is the work done, right? Now let us say that both the heat and work done are the forms of energy, right? And when this is happening, the internal energy E also varies, also changes, right? So let us say if the internal energy changes because of this process, we can say that the dE is the change in internal energy, right? So if we say that the energy is conserved, then we can write dE is the change in internal energy is because of the change in heat plus the change in work done, right? Right? So this is actually the statement of first law of thermodynamics. Anyway, we will discuss. Now, you have a system, you have a surroundings, you are supplying heat, and there is a work done, and there is a change in internal energy. Let us apply this to the fixed control volume, right? So let us say the fluid is flowing through the fixed control volume. Let us say fluid is flowing through fixed control volume. Let us say what are all the things happening, right? So we know the control volume, right? In the previous classes, we have discussed about the control volume, right? So I hope you remember that the control volume, the diagram which we have drawn in the continuity equation probably. So we have the say the fixed control volume in a space, and we have made the control volume as dV, and we have a surface, right? Surface S, and Then we have made some surface on the fluid volume. Then we said this is ds and this is moving at a velocity v, and again the perpendicular to that per unit area, that ds we have taken, and this is a whole control volume v, this is a whole surface s, and ds is a elemental surface, dv is a elemental volume, and all those things we know. Now when the fluid is flowing through the fixed control volume, by discussing about the temperature, we can write three terms. One is, say A is equal to rate of heat added to fluid inside the control volume from the surroundings, right? So the amount of heat added to the control volume to the surroundings, then because of the supply of heat, you have a work done. So let us say rate of work done, the rate of work done on the fluid inside the control volume. Now, so this is equal to the rate of change of energy of the fluid as it flows through the control volume. There we have considered that as the internal energy. So let us write rate of change of energy, rate of change of energy of fluid as it flows through the control volume. So we can write this as the equation, same equation. Here dE plus dE is equal to dQ plus dW, and here we can write A plus B is equal to C. Now let us think one by one. In this equation, if you consider all the terms or the time rate of terms, right? So we can say that time rate of work done and all those things are actually mentioned as power, right? Anyway, so let us consider the equation, right? So the rate of heat added, right? The first one is A. So let us write the term A. What is A? A is rate of heat added to the fluid inside the control volume. So I can say that this can be written as volumetric heating. Volumetric heating. Right? So volumetric heating inside the control volume. Volumetric heating inside the control volume. Control volume. Right? So we can say that the volumetric heat addition per unit mass is usually and the notation is Q dot, right? And the unit is the joule per second kg, right? So we can write now that the mass contained within an elemental volume, because our ultimate goal is talking about elemental volume, right? So let us write the mass in the elemental volume is rho into dV. Right? Here I can write mass. So mass contained in the elemental volume is rho into dV. So you see the mass, and then we can write this equation: rate of volumetric heating. The rate of volumetric heating is equal to triple integral over V Q dot rho dV. Right? So I will write this equation as here, this equation as 1, and we need to prove the equation 1, and this equation is 2. So rate of volumetric heating can now defined as triple integral over volume V Q dot rho dV. So what is Q dot? Volumetric rate of heat addition per unit mass, right? Volumetric rate of heat addition per unit mass, and rho into dV is the mass contained in the elemental volume. So rate of volumetric heating can be expressed as the equation 2. Now the volumetric heat addition, again this increase in heat can be given by various means. One such mean is the viscosity, right? So let us say viscosity, because of viscosity, you can feel that when you travel in a car from Tanjore to Trichy, even during the very cold season, cold winter, you can experience this. When you land at Trichy and when you touch the surface of your car, you can feel the temperature. The temperature will be a significant temperature, right? And that is because of the flow over one layer of air to another layer, and the temperature is because of the viscosity. So because of viscosity, that is viscous contribution, we are not very much interested to go deeper into the viscous effect now, since we will discuss that little later. I will write viscous, the volumetric heating due to the viscosity, I just write Q dot viscous. So the A can be written as the rate of volumetric heating over volume, that Q dot rho dV plus Q dot. So this is due to the heating. Now the rate of work done, that is what the second point, right? So let us discuss the second point, rate of work done. Rate of work done. So we know that at a time t, say let us say I have one particular body at time t. At time t, it is located at this particular position. Say I mentioned this as R1, and it moves to some other location at time t2. Say this time t plus dt, right? It moves from this point to this point. Say let us, for our convenience, we will write this as R2, right? This is R1 and this is R2, and this element moves from here because of the force here. Okay, so force exerted on the moving body. So here we need to write the rate of doing work on moving the body. Let us write the rate of doing work on moving body. That is equal to the force F into V, right? In other words, we can say the rate of work done on a moving body is equal to the product of its velocity and the component of force in the direction of the velocity, right? Then we can write these. Okay. Now, let us consider the ds. ds is the elemental area that we know, right? So, when we say that the pressure force, the force, whenever we consider a force, it can be a pressure force. So, pressure force on the element, what element? ds, can be written as minus p ds, and the symbol, it doesn't matter because moving away or moving towards the system, right? Then if this is the pressure force, then the rate of work done, right? The rate of work done which is given here, we can write this as P into ds. P into ds into V. Now, if we consider the pressure force, the rate of work done, let us say the rate of work done on the fluid volume V due to the pressure force. Due to the pressure force acting on the surface, yes, then we can write this as double integral over the surface, yes, PdS into V. So let us write this equation as 4. So rate of work done is force into the velocity, and here the pressure force, because of the pressure force we have considered. Now you may ask a question, okay, we have considered the pressure force, how about the body force? Now let us consider the body force. So I will write directly the rate of work done on the fluid inside the volume B due to body force. That is equal to triple integral over V rho F dV into V. Right? This is the body force that we know already. And again, we can again write that the contribution of the viscous force. So let us write the contribution of the viscous force is W dot, and hence we can write the whole equation 5 and this is 6. So 4, 5, 6 can be written as B, that is the work done component, right? The B is the work done component. The work done component is because of the first one is the work done due to the pressure force plus body force rho F dot V into dV plus W work done because of the viscosity. So I will write this equation as 6. Now we know these two components, A and B we know. Now we need to calculate C. So let us write the C. I said, what is C? C is the change in internal energy, right? So the internal energy E is due to the random motion of atoms and molecules, right? Random motion of atoms and molecules. Atoms and molecules. Right? So we can write the equation for that. Right. So we know that the kinetic energy of, okay, I will write kinetic energy per unit mass so that we will not write that n. Unit mass is equal to V square by 2, right? So energy per unit mass of the moving fluid, I will write energy per unit mass of the moving fluid is the summation of internal energy plus the kinetic energy. Internal energy is also the E is the internal energy per unit mass. V square by 2 is the kinetic energy per unit mass. Right? So this is the total energy. Okay. So now we can write the expression C. Right? So the rate of change of total energy of the fluid as it flows through the control volume. Right? So we can write, we already know the elemental mass as usual. The elemental mass across ds, write this elemental mass across ds. So elemental mass is rho b ds, right? So elemental energy flow same across ds is equal to rho v ds into E plus V square by 2. Right? So I will write the other equation also. Say the net rate of flow, net rate of flow of total energy. That is equal to double integral over S rho V ds into E plus V square by 2. So this is supposed to be the equation number 7. So we got the equations. A, B and C already we have, right? So this is supposed to be the C, right? So we have now the 3 components. Now, what happens if the flow is unsteady? That is time rate of change of total energy. How can we express that? The unsteady component, right? So let us write the time rate of time rate of time rate of change of total energy time rate of change of total energy inside the volume, the whole volume, right? So we can write dou by dou t triple integral over V. Right? Here we have taken the net rate of flow of total energy is 7, and you remember in the momentum equation we have considered the time rate of change of momentum. Similarly, here time rate of change of total energy, that is due to the transient fluctuation transient fluctuation. So we can write this directly. We can say rho E plus V square by 2 into dV. Right? This is equation number 8. Here in the rate of change of energy, we will consider 2 component, equation 7 and 8. So I can write this as C. This is the C1 probably, and this is C2. So the total C I can write dou by dou t of triple integral over V rho into E plus V square by 2 into dV plus double integral over S rho V ds E plus V square by 2 into d. So this is equation number 9, and now we can write A plus B is equal to C. So what is the physical principle as we stated in the beginning of this derivation? The rate of change of the rate of heat added to the fluid plus the rate of work done. The rate of heat added to the fluid to the rate of work done is equal to the change of total energy, right? Is equal to the change of total energy of the fluid flows through the control volume. That means that the energy is conserved, right? So A plus B equal to C. Now we will write the full energy equation. Say triple integral over V q dot rho dV plus that viscous term Q viscous minus double integral over S PV ds plus triple integral over V, the body force rho FV dV plus the work done due to the viscous component, that is equal to the change in total internal energy due to the transient fluctuation, that is with respect to time t, is rho into E plus V square by 2 into dV plus the double integral over S rho E plus V square by 2 into V into S. So this energy equation, this is the total energy equation, right? So you can write this equation. So this is the energy equation. So this is the energy equation in integral form. Right? So as usual, we do some, we reduce this equation as usual, right? So if we want to reduce this equation, say for example, if we want to consider the flow is steady. So if the flow is steady, this term will go zero, right? Say for example, flow is steady, then I say dou by dou t component becomes zero, right? And I say the flow is inviscous. So if it is inviscous, Q dot viscous is equal to W dot viscous, and both will be equal to 0. That means this component will be equal to 0 and this component will be equal to 0. Right? So this is the end of the energy equation, right? And the equation can be further reduced based on various other assumptions, right? So with this energy equation, we have introduced the variable E, right? E is the internal energy, right? Now, what are all the variables we have? We have rho, density, pressure P, velocity V, and the internal energy E, right? So we have 4 unknowns, but we have only 3 equations: continuity equation, momentum equation, and energy equation. And hence we use the thermodynamic relation to express E is equal to CVT. What is CV? In the thermodynamics, you might have studied, right? What is CV? Specific heat at constant volume, right? So we have E also. And what about T? We have again E and we have T. How to place this T? Again, we have another equation, right? What is that equation? P is equal to rho RT, right? So this is the equation of state, perfect equation of state. And finally, we can have 5 unknowns, 5 equations, and we can solve nicely. So this is the energy equation. We will go through it once again. So we start with the physical principle. Energy can neither be created nor be destroyed, but it can be converted from one form to another. And I have considered the system and their surroundings. And inside the system, there are various atoms and molecules inside the system. And del Q is the incremental amount of heat. And when the incremental amount of heat added to the system, there is a work done del W. And because of the heat and the work done, there is a change in internal energy. So the law of energy, conservation of energy, right, is done. So we apply the same equation, same principle to the fluid element dV, and we consider first the rate of heat added to the fluid, and then the work done to the fluid, and then the rate of change of internal energy. So first one, the volumetric heat addition inside the control volume. So we have considered the rate of volumetric heating and the heating because of the viscous nature. So 2 and 3 contributes A. Then rate of work done from moving one particular body from one point to another. So we say that rate of doing work on moving a body is F into V, the F due to pressure force, and again F due to body force. And again the work done because of the viscous flow, we consider W dot, right? So by this way the work done is given by B. Third point, the volumetric heat, the energy, right? Change in internal energy. So we consider first the internal energy, random motion of the atoms and molecules, and the kinetic energy. And this is the net rate of flow of total energy. And again, another one is the flow, the energy, change in energy due to the transient fluctuation. So what is that transient fluctuation? You take a property of the element, right? When you take a property of the element, it will be varying with respect to time. So this particular property is considered. So dou by dou t we have considered. With respect to time, it changes, and hence we consider dou t. So the final equation C is this one as shown in equation 9. Once we know A, B, and C, we have written the whole energy equation. So this is the energy equation in integral form, right? So we need to remember this one. See what are all the components involved in the energy equation. And when we try to reduce this equation, we understand that if it is unsteady case, dou by dou t has a significant value. And if it is a viscous, if it is a steady case, we can consider dou by dou t is equal to 0. If it is an inviscid flow, Q dot and W dot become 0. And then we have the equations involves the parameters rho, P, V, and the internal energy E and the temperature T. And we have another two equations. One is equation of state and one is E is equal to CVT. So from 5 unknowns and 5 equations now arrived, right? So this is all about the energy equation, right? So I stop at this point, right? Thank you very much.